Hello and welcome. My name is Brian Menunos, and I work with the Hackeye Institute. I'm also a university professor at the University of Northern British Columbia. I've been extremely fortunate to have worked with Chief Blaney, Eric Blaney, and others on an event that happened in your territory last December.
Hi, I'm Marten Geertsma. I'm a research scientist with the Ministry of Forest, Lands and Natural Resource Operations, and I'm also an adjunct professor at UNBC, the same university as Brian. I'm also very happy and thankful to be working on this project.
What Martin and I would like to do today is to take you on a journey, tell a story, if you will, about events that happened in your territory last December. The event that we'll be talking about is a large landslide and flood that occurred in Elliot Creek. I understand that the Homalco people refer to themselves as the people of fast running waters. Well, our story today, as you'll see, involves lots and lots of fast moving water, rocks and mud, and glaciers too. In order to understand what happened at Elliott Creek, we first have to go back in time, way back when ice covered all of the British Columbia landscape. If you wanted to have an idea what the landscape looked like about 18,000 years ago, then we can travel to the Greenland ice sheet. This is an image taken from an aircraft from NASA, looking at the actual ice sheet and the topography that sticks out along its edges. And this would have been very similar conditions to what existed in our own part of the world. So vast amounts of ice covering many, many hundreds of meters deep ice, covering practically all of the landscape and flowing out to the coast itself. So what's the connection between continental glaciations and the landslide that took place at Elliott Creek? The connection is that through repeated growth and demise of these ice sheets, the topography or the land beneath this ice would have been sculpted by glaciers themselves. And that's hard to understand because when we think of ice, it's quite a soft material. But in some situations, that ice can freeze onto the underlying bedrock, plucking away this rock. And over time, this plucking or quarrying can deepen valleys much faster than they can widen. I'm going to walk through a series of illustrations to give you an idea of what might have occurred at Elliott Creek and how it may have looked about 5,000 years ago. So in this case, the topography was gentle. There wasn't any ice on the landscape. As glaciers grew throughout the mountains and northern environments on our planet, these glaciers first formed in high elevations, and they would descend down to lower elevations, in some cases getting hundreds of meters thick. And as they started to cover that landscape, areas underneath thicker ice would tend to concentrate areas that you would actually start to sculpt and move away rock itself. Sometimes when those ice sheets disappeared, the ice was limited to highest elevations or into deep valleys from which the ice flowed from those high topographic regions. And there, and in those depressions, glacier erosion continued. And over time, those glaciers, being concentrated in those valleys, would deepen these valleys faster than they would widen. And that's one way that you would actually get these U-shaped valleys. And with rapid ice retreat that's taken place over the last 50 years, this exposes and can expose steep, unstable rock, which was formerly supported by the ice itself. So we're removing that supporting structure of the ice, exposing and allowing those unstable slopes to perhaps suddenly fail. And this is what we think had happened at Elliott Creek. With the removal of that supporting ice, we had an unstable hillside which suddenly let go. And as Martin will describe, one of the important aspects, or why this was so catastrophic, if you will, was simply because we had the presence of a lake below this slope into which this material could suddenly fail.
Yeah, thanks, Brian. And that's exactly the thing. Without this lake, we wouldn't have had this catastrophic event. And we'll come back to that a few times. So in the next few slides, we will see how Elliott Lake grew in size and followed a retreating glacier up the valley. So this is Elliott Lake in 1965. And when we look at the next photo from 2021, we will see that the lake is much bigger and that the glacier is further back in the valley. And indeed, we see that here. So the lake has grown a lot. The 2020 landslide was enormous. Not the biggest one in BC, but it's still about the same as if all the cars in Canada had fallen from the mountainside at once. And we see this zone in red on the hillside, and it deposited on the glacier in the blue area and also filled the lake in front of this blue area. And you can see some little islands in the lake that are where much of this material has come. These lines that we see are different positions of the snout of the glacier. And so we could see that, yeah, in the last decades, it moved back very quickly. So, and like I want to keep repeating, is that the lake makes all the difference to this story. There would have been no tsunami, no flood, just a rock slide. Kind of a no big deal rock slide because it was so remote. In fact, an earlier landslide had happened, but it landed on the glacier without causing a flood. What I'm going to show you next is an animation made by one of our colleagues of the rock slide and the wave using a computer model. So don't really worry about the numbers at the bottom at the scale, but look at the time on the top. This landslide was moving at 180 kilometers an hour when it hit the lake. And the tsunami wave in the lake was moving at about 125 kilometers an hour. And I'll just play it now. So here we see the landslide detaching from the lake, from the slope. And it takes about 30 seconds for it to reach the lake. And then we see a series of waves happening. And this leading wave reaches the outlet of the lake about 90 seconds after the landslide happened. And then it spills over the edge of the lake and bores down the valley. Let's look at the size of this landslide and flood. And I like to explain things in dump truck loads because I like dump trucks. So we had about 2 million dump truck loads equivalent of material hit the valley floor. Some of it stayed on the glacier, but about 1.3 million dump truck loads went into the lake. And if you look at the red arrow, you can see some islands of this rock slide deposit in the lake. So the lake is very much filled with this material. So can you imagine all these loads coming at you at the same time at about 180 kilometers an hour? It's really unbelievable, except we could see the evidence on the shore of the lake. So the force of that material entering the lake created a tsunami wave that was close to 115 meters in elevation, or about 375 feet high. Again, that's marked by the yellow line. And this wave also caused a lot of the water to leap out of the lake. It took about a minute and a half from when the landslide started to where most of this water left the lake to roar down Elliot Creek. And here we see the aftermath of this event. This is from on one of our helicopter flights. The forest used to grow to the lake shore. It's gone. There's nowhere to be seen. These islands weren't here before. These islands are rock slide deposits. And then when this water left the lake, it wasn't confined to this little channel. That channel couldn't handle it. It spilled out through the valley, and we'll look at that later, but it's continued to create a lot of damage all along, destroying forests. So in some places, this flood traveled up to 180 kilometers an hour. Not everywhere, but in some places it went that fast. And it took about 10 minutes from the floodwaters to leave Elliott Lake and to come to the fan on Southgate River. And it rearranged the creek a lot. In some places, it eroded more than 40 meters deep. And so we measured how much sediment was lost by the flood. How much sediment was lost in about 10 minutes of flooding. And it's the equivalent of about 400,000 dump truck loads that left Elliott Creek, went into Southgate River, and much of that into Bute Inlet. And so remember that, again, I'll repeat it, without this lake, the flood wouldn't have happened. So we're going to look at another animation made by one of our colleagues from California. And I want you to look at the time in seconds at the top of the screen. I'll play this. So here you see the tsunami wave on Elliott Lake spilling over into the creek. Of course, the creek is far too small to accommodate all that water. So it spills over the edges, bores down and erodes the creek bottom, like we said, up to 40 meters. Sometimes it travels as fast as 180 kilometers an hour. And it travels that distance from the lake to the fan at the bottom in about 10 minutes. It's a crazy flood. So one of the things that we try to answer and try to study with these types of events, could we have predicted this? And can we predict future events? So we've got some of our colleagues to analyze satellite images and study them in detail and compare a whole lot of them together. And from this, we can determine that, well, this slope was actually moving a little bit already. And then the year before the landslide, it moved even more. And so we see this from certain types of satellite images, but also from the radar images. And in fact, this part of the slope is where our landslide occurred. And in the summer of 2020, that slope was deforming more rapidly than the surrounding slopes. So that can give us a bit of a clue. It's not easy to do because sometimes we have this type of deformation and nothing happens. And sometimes we have catastrophic landslides where there's absolutely no warning. So it's a complex issue. But what we need to know is whether these things will happen again. And I'll hand it over to Brian here.
Thank you, Martin. So the events that Martin just described were clearly exceptional in their power and unfortunately in their impact that they had on the ecosystem and specifically the salmon-bearing waters in your territory. An important question to ask is whether such an event would happen again for Elliott. We don't think it would, and that's simply because the presence of Elliott Lake and allowed this flood to be so large, so catastrophic, well, that lake is now filled in large part with debris. But we have to consider that it's not just Elliott Creek, but there may be other regions where these sorts of events can happen. And so, what are those conditions that we need to worry about? We first need, in terms of these events to occur, we need rapidly deglaciated terrain, so rapidly retreating glaciers. We need the formation of lakes, and we also need the presence of unstable terrain surrounding those lakes. What I want to do is I want to show you an example of some work that was done several years ago on how glaciers themselves may be expected to change under a moderate emission scenario. As we walk through this simulation, the white covered areas, these are glaciers. These are the glacier ice. And you'll also see some areas that are pink. These represent accumulation zones on the glaciers. You can think of these as where the seasonal snow from the previous winter lasts throughout the year. And you can imagine that if year after year, those areas of winter snow accumulation get progressively smaller, then those glaciers will thin and rapidly retreat. Just to give you an idea of where we are, this is Elliott Creek. Up here, this is Mount Waddington, where the northern winds blow from. And then this is also the time on the upper right as we move through this simulation. So here you can see the areas of pink, which represent that seasonal snow. And as we move through the remaining bits of this century, we see that those areas are projected to get considerably smaller. You can also see the lower elevations of these glaciers retreating away as those accumulation areas become less and less. In terms of understanding whether a similar event like Elliott Creek would happen, requires us to look at the existence and likelihood of the existence of lakes and the likelihood of landslides entering those. And that's work being currently worked on by one of our key collaborators, Tom Millard, who also works for the ministry, the same ministry that Martin works for. Tom will in fact present as the next speaker in the speaker series. In addition to the work that we can do for present day glaciers, we can also use a simple way to estimate where lakes might form under present day glaciers. This is an example or a cartoon showing a cross section of a hypothetical glacier with distance on the x-axis and elevation on the y. And largely because ice deforms under its own weight, what we often would expect to see is that areas of steeply sloping ice tend to move fast and they tend to have thinner ice, whereas areas underneath gently sloping ice tend to have much thicker ice that piles in a location and tends to have much thicker ice, but also in some cases depressions that are below the ice itself. And so by mapping the ice elevation and the distribution of ice, in some cases we can actually get a snapshot of where we might expect to find depressions, these areas of topography that may be future sites for lake formation. And so by using simple techniques, we can actually map the presence or the likely presence of these lakes going forward, and then combine that information with steep terrain to come up with a hazard planning for the likelihood of future events happening in areas that are undergoing deglaciation. I'm going to turn it back to Martin to summarize.
Yeah, thanks, Brian. It's very important to find out where those lakes are, because our mountains will continue to lose glaciers. When glaciers recede, the slopes above them often lose strength, and this can make them vulnerable to failure, as we've seen at Elliott Creek. And sometimes lakes will follow these glaciers, and sometimes those lakes grow in size. And, and the lakes can travel to the more unstable parts of the valleys as well. It's not that big of a deal when a landslide happens on a glacier alone. We just had an example in July of a 7 kilometer long rock avalanche to the north of Stewart, and which happened during the summer's heat dome. But only the very tip of this catastrophic event reached a lake. So there was no big wave and no flood. But when we get a direct hit into a lake or into the sea, the destruction can be very far reaching. So let's say a landslide travels 5 kilometers. The destruction from it can be 25 kilometers, for example. New research, new computer simulations, LiDAR, satellite analysis, all of these things will help us predict these sorts of events. And even though the hazard is likely to increase in places, perhaps we've seen the worst at Elliot Creek. The lake has much less water than before the landslide. If another landslide entered the lake, the flood coming from the lake, even though it would still be very dangerous, would probably be much smaller than the one that happened in 2020. So identifying hazards with existing lakes in the territory is important, and that's what Tom Millard will discuss next. Thank you very much for your attention.
Thank you, Martin. And we both would like to thank all of you for watching our short summary, and we look forward to meeting you in person in several weeks. We'd also like to acknowledge and thank our many collaborators who are doing work on the Elliott Creek landslide, both in terms of the event itself, but also the implications as that water and sediment flowed into the Southgate River and into the fjord itself. We also would like to greatly thank the help of the Hackeye Institute and many of our collaborators there with some of the graphics and the recording and the presentation. So thank you very much. Have a great day, and we will see you in a few weeks.